Third and final speaker today is Sam Ketchum.
Good morning, everyone. For my senior capstone internship, I worked at ALS Therapy Development Institute. It's a research foundation in Cambridge that's fully invested in finding a cure for ALS, also more commonly known as Lou Gehrig's disease. ALS is a terminal neuromuscular wasting disease, which means that the motor neurons inside your body, they get inflamed, they build up proteins inside and shut down, causing other motor neurons around them to shut down and eventually paralyzing someone, taking away their ability to breathe until they pass away. This, on average, takes 2 to 5 years. And worst part about it is there's no known cause, so we don't know why it happens, and there's also no known cure. Unfortunately, in 2010, my father, Todd Ketchum, was diagnosed with ALS. He is still fighting strong, has been ever since. My family is doing everything we can to try and find a cure. So that's why I'm showing so much interest in ALS research and ALS TBI. Oh, wrong way. So neuromuscular degeneration. There are thousands of motor neurons inside your body that reach from your spinal cord to your muscles. Some can even be as long as a meter because they need to reach all the muscles in your body. So they can reach from the bottom of your spinal cord to a toe, or out from the back of your spinal cord to your fingers. And that's just one cell. And inside these cells, proteins, when they misfold and change their shape, can clump up and aggregate and cause the motor neurons to shut down. It varies from patient to patient how long this process takes. Some people can only battle ALS for 8 months. Others battle ALS for over 50 years. And it also depends, it varies on where the disease can start. Some people it starts in a left hand or a right foot. Others can have bulbar onset, which means it starts in your upper general head region. ALS awareness. May is actually ALS Awareness Month. Fenway will hopefully be doing an ALS Awareness Night because of Lou Gehrig. Lou Gehrig was a New York Yankees baseball player, a great baseball player who was cut down in his prime from ALS, had to retire because he was getting weaker, and then eventually passed away a couple years later. Currently, there's only 35,000 people in the US diagnosed with ALS, and compared to cancer, which is 13 million, doesn't sound like very much, but that's still a very, very large amount of people. Unfortunately, this deems it an orphan disease, which just means that it doesn't affect enough people for it to be a big headlining problem. Some public icons, like I said, Lou Gehrig, passed away from ALS a very long time ago. Steve Gleason, you may have heard of him. He was a football player for the Saints, had to retire because his arms were getting weaker until, and then in the following year he was diagnosed with ALS and has been battling it ever since. He has a foundation called No White Flags. It's a really cool, he's a really inspirational guy with a really cool story. And also Stephen Hawking. Not many people know this, but Stephen Hawking has ALS, has for 52 years. He's the longest I've ever heard of anyone living with ALS, which is really cool, and I'd like to see people living that long in the future. So this is a picture of the lab that I worked at, ALS Therapy Development Institute. It's the first ever nonprofit biotech in the world, which is a pretty big deal, and they're also one of the leading research labs in the world on ALS therapy. They're completely 100% focused and invested on raising ALS awareness and trying to find a cure for ALS. It's a really, really great community there too. The diagnosis process for ALS, it's kind of a worst case scenario thing. There is no genetic test that you can go and take that tells you do or do not have ALS. So you go and you get tested for Lyme disease. From my personal experience with my father, it took 1 year for him to be diagnosed from when he started showing symptoms. He was diagnosed with Lyme, with MS, with possibility of multifocal neuropathy, a bunch of other stuff that I don't even know, until eventually his doctors told him that he does have ALS. So there are two main versions of ALS, or two versions of ALS, and I'm hesitant to say this because the only difference between these two versions is that one is genetic, you can inherit it, the other is sporadic, it's completely random. We don't know why it occurs. The sporadic ALS, SALS, makes up approximately 90% of all ALS cases, and FALS includes the other 10%. We've been able to study FALS a lot closer because we can look at both generations who have had the disease and eliminate some variables and find out which proteins are misfolding, or we think are misfolding, and create models that we can test different possible drug treatments against. So, like I said, in the motor neurons, proteins misfold, and there are thousands of proteins in your cells. Specifically, in your motor neurons, there's a protein called superoxide dismutase 1, more commonly referred to as SOD1. It's what I mainly focused on for my project at TDI. So far, there have been 27 proteins that have been discovered that can possibly cause ALS, but SOD1 was the first. SOD1's original function is to find free radicals inside your cells, which are just little bad particles that you don't want there, and dispose of them. And when SOD1 misfolds, it changes its shape, and with proteins, shape dictates their function. So not only does it not get rid of the free radicals anymore, but it tends to clump up and stick together. Specifically with SOD1, well, all proteins are made up of amino acids. They're the building blocks of the proteins, and depending on what order they go in, that decides what protein it is. In SOD1, there are 4 amino acids called cysteines, and these cysteines are very unique because when SOD1 does misfold, these cysteines can create covalent bonds, which are really, really strong, and we think that's where the aggregation is occurring from. Bottom left is a diagram of the SOD1 particles sticking together, the cysteines. And this is another diagram. Up top, you can see just a regular SOD1 particle, and then some aggregation, and then just a big aggregate clump at the bottom. So for my experiment that I carried out with lots of help from others at TDI, this is pretty much a diagram that describes it. We took the spinal cord from a G93A SOD1 mouse, which just means the spinal cord from a mouse that has a disease that looks a lot like ALS. We're not sure if it is because we don't know exactly what ALS is, but we have a rough idea. And we homogenized that spinal cord into a solution, just made a universal in solution, and then spun it around in this machine in the top right corner called a centrifuge, which is just the kind of thing you see in movies that spins vials around really fast. And so from that, we got the protein lysate, which is just, it's what's left. All the big chunks drop out to the bottom. And then we put that into the freezer, let it incubate with the drugs, and then afterwards put it through a filter trap, which is this thing right here. And so a filter trap is basically a high-tech vacuum that sucks the lysate through a sheet of paper, and the aggregates get stuck on that sheet of paper, and then we're able to look at how much protein has aggregated. So for my experiment, we wanted to stop or slow down aggregation from occurring by mixing in a chemical called iodoacetamide. It's a highly toxic chemical for humans. If inhaled, it will kill you. So we can't give that to just the general public, but we're trying to find a drug that will act like it. So we put the iodoacetamide into the spinal cord lysates at different concentrations, had a couple controls, and we did this because in the past it's been found that if you put a spinal cord lysate into a minus 80 degrees Celsius freezer, aggregation is completely stopped, or nearly completely stopped, and if you put it into a minus 20 degrees Celsius freezer, aggregation will be expedited. So that gives us something that we can test possible treatments against for the aggregates. So, and this is a visual that I came up with, just a puzzle. If you imagine just the center puzzle piece as like the beginning of a SOD1 aggregate and the half pieces as the drug, they come in and block off the cysteines, the possible locations for more aggregation from occurring. So the results from the experiment. The controls, thankfully, acted as expected. We measure the amount of aggregation in luminescence because you can't see the aggregates, they're too small. So we put on a chemical that sticks to the aggregates and then put on a chemical that'll make that last chemical glow. And based on how much it's glowing, we can tell how many aggregates are there. So the control at minus 80 was roughly under 2,000 luminescence. The control at minus 20 was roughly under 6,000. Unfortunately, I do not know why the 6 millimolar and 20 millimolar concentrations acted the way they did. They actually increased aggregation beyond the minus 20 control. I'm not sure anyone knows why that happened yet. We're still trying to figure that out, but it's a long process. The 60 millimolar concentration is what I want to focus on, that was kept at the minus 20. It nearly stopped aggregation from occurring, which is exactly what we wanted to happen. And so we believe that the iodocetamide was able to go into the protein lysates quick enough, and there was enough of it to the point where it was able to block off the cysteines and stop aggregation from occurring. And like I said, if iodocetamide wasn't a deadly toxin, then we'd be handing it out to ALS patients as we speak. But unfortunately it is, so we have to find something that will act like the iodocetamide in blocking the cysteines. So finally, I would like to say a big thank you to everyone who I worked with at TDI for dealing with me and accommodating me for the past couple months. And a special thanks to my coworker, Alan. He's the other intern at TDI who struggled through all of the testing with me and stuff. So thank you all for coming.